All right, I want to find the mass moment of inertia of this solid about the y-axis, okay? And I know that it has a total mass of 1,500, and we'll get to why that's important here in a second. The thing I'm going to do here is I'm going to break this up into thin disks, okay? And then add those up. So the thickness of these disks, or an arbitrary disk, will be dy, okay? And the radius will be basically up to that curve there, which will be z. Okay. Now, again, remember the equation that I'm going to use to find this. The moment inertia of that thin disk is 1/2 mr squared, where m is going to be dm, and then r squared we'll talk about in a second, right? So I need to find dm on this guy. And again, dm is rho times dv, where dv is going to be pi r squared times the thickness, where r is z and the thickness is dy. Now the thing is I don't know what rho is, but I do know the total mass of this guy here, right? So again, you'll remember that density is mass divided by volume. So if I can find the volume, okay, then I know the mass. If I find the volume, I can find rho. So let's go ahead and figure out what the volume would be, right? Where the volume is going to be basically the integral of dv, basically sum up all of the volumes of this thin disk, right? So instead of dv, I'm going to use pi z squared dy. That's what dv equals, again, but now I'm going to integrate with respect to y here. So I need to use, instead of z squared, I want to use 1/16 y cubed, because that's what z squared equals. That's the equation of that curve there, dy. And now I'm integrating with respect to y, so I'm going to start at 0, go out to 4 along the y-axis like that. From this, I can find that the volume of this guy, once I do that integral, is going to be 12.6, and that will be cubic meters. So now I can find rho is 1,500 divided by 12.6, which equals 119, and that's going to be kilograms per cubic meter. So now I have rho for this value. So now I can go ahead and plug in what I know. Go back to my di equation. That's the moment of inertia for my thin disk. Okay, and I'm going to plug in dm. And again, dm is going to be rho pi z squared dy. Okay, and instead of z squared, I'm going to use 1/16 y cubed, because it tells me z squared equals 1/16 y cubed. Okay, and then that's times dy. So now I have a bunch of constants, okay, and I can integrate with respect to y. So let's go ahead and integrate both sides. So to find the moment of inertia about the y-axis, I'm going to integrate, and then this will be 1/2. Rho is 119. We've already calculated that, times pi times 1/16 times you know what I forgot here? I forgot, let me squeeze it in here, r squared, where r squared, remember, is z squared. So that means all of this stuff is actually going to be squared. Okay. Um, and again, the reason for that is because unfortunately, I just had the dm in there. I need to also include the r squared, this r squared value right there. Okay, that's z squared. So it's basically z squared times z squared, which is going to be that 1/16th times y cubed, all of that squared. It's basically z squared squared, right? So again, I'll put that right there because that's what z squared equals, okay? And I've got two of them, so they throw in there like that. So I apologize for forgetting that. Hopefully that made sense. I'm going to, again, integrate this with respect to y from 0 up to 4. Okay, when I do that integral, I get 1714, and this will have the units of kilogram, meters squared. Weird units, but that's what the units are. Okay, so again, I take the time to find my density. Once I have my density, then I can find dm of my thin disk. Then knowing that a disk has a moment of inertia of 1/2 mr squared, I then use that, where dm is going to be rho pi, this chunk right here. So 1/2 that dm, which is rho times dv, okay, times r squared, which for our case, the radius is z for that disk. So I forgot that the first time, throw that in again, simplifying a little bit, putting what I know, getting everything in terms of y, I get that next equation where I've got basically y cubed over 16 squared. And again, that's because I've got z squared squared. So I throw that in there. Okay. Then from that, I can go ahead and plug everything in, do an integral from 0 to 4 because I'm integrating with respect to y to find the mass moment of inertia of this solid.